I'm Tyler.
I'm Liam.
And this is the Biomechanics of Kicking a Soccer Ball. So, a brief history of soccer. It began in 1863 in England when rugby football and association football, or soccer, branched off on their different courses, and the Football Association in England was formed. It became the sport's first governing body of soccer. Now, more than 265 million people around the world play soccer regularly. And we're going to be focusing on kicking a soccer ball. So a little bit of background with that. Adults on average can kick the ball approximately 60 miles an hour, while professionals have recorded kicking the ball upwards of 90 miles an hour. The three mechanical components of kicking a soccer ball that we're going to focus on today are the joint angles of the kicking leg, which includes the optimal angles of the knee and hip, the momentum-impulse relationship during the contact of the foot with the ball, and then torques. So when you're kicking a soccer ball, there are 4 stages. The first stage is a backswing, the second stage is a leg cocking, third stage is a leg acceleration, and the fourth stage is follow through. So we're going to look at these 4 stages and compare how the optimal angles go into these motions. So during the backswing phase, the kicking leg moves backwards with the hip extending up to 29 degrees with a velocity of 171.9 to around 286.5 degrees per second. So you have quite a bit of speed when you're pulling your leg back to start this kicking motion. So next we're going to go on to leg acceleration. We're just going to skip over leg cocking because the leg acceleration is what's really contributing to the torque about the hip and the knee, which goes into kicking the actual ball. So the forward motion is initiated by rotating the pelvis around the supporting leg and by bringing the thigh of the kicking leg forwards while the knee continues to flex. So you can see in the picture of Megan Rapinoe, her thigh is coming forward and is almost even with her other leg, but her knee is still flexed with her leg, her shank behind her. So the hip starts to flex, reaching values of 20 degrees at speeds of up to 745 degrees per second. And as it's flexing, the knee simultaneously starts to extend, and that velocity is maximized at about 860 to 1,720 degrees per second. And the last phase we're going to look at is still kind of leg acceleration and then the follow-through. So as the knee starts to extend, the angular velocity of the thigh starts to decline, but the shank velocity increases linearly until the foot makes contact with the ball, reaching values of 1,891 degrees per second. So as you can see in the picture, the thigh remains in relatively the same place, so that's at the end of when the velocity is decreasing. But as you can see, the shank is moving, and that velocity is increasing linearly throughout that whole motion. So you can see the picture on the left is right as ball contact is made, and then the picture on the right is the follow-through. You can see that, the thigh is in the same spot, but the shank has continued to move. At the ball impact, the thigh angular velocity is almost 0, and so that's why you see the thigh in the same spot. And the shank and the foot reach peak angular velocity and 0 acceleration. And the 0 acceleration is because the velocity is remaining constant, so it's not that the foot stops, but so the velocity is not changing over time.
Okay, so now we're going to move on to talking about the torques. First, I'm going to talk about the optimal position for kicking a soccer ball. When evaluating a kick quality, researchers concluded that the maximal distance between the kick side hip and the non-kick side shoulder provided a quantitative means of judging the quick kick quality. In order to create a larger distance between the two, the hip must abduct more, creating a larger radius of gyration and therefore a greater torque for a given force. During an instep kick, the hip is the primary mover, contributing to more to the angular acceleration of the shank than the knee. In a side foot kick, however, the knee has a higher power, likely due to an effort required at the hip to maintain the foot position. A strong relationship exists between the foot swing velocity and the resultant ball velocity. So now we're going to do a sample calculation for hip torque. So we sketched out a leg kicking a soccer ball in the initial and final states. The initial is at the peak of backswing, and the final is the leg making contact with the ball. Our angles for initial is 29-degree extended hip, and then the knee 110 degrees from the y-axis. And then in our final, which is 0.5 seconds later, it's a 29-degree or flexed hip, and then a knee that is parallel with the y-axis. So our radius gyration for the initial is 0.3 meters and final is 0.6 meters. And then we have our masses of the shank are 4.6 kilograms, and then for the hip it's 7.5 kilograms. And then we combine those two for the hip torque calculation because the hip is moving both shank and thigh. So first, in order to solve this, we looked at solving for the inertia, which is mass times radius of gyration squared. So we did 12.1 kilograms times 0.3 meters squared. And then we did this for initial and final. And then we solved for angular velocity, which is the change in the angle over change in time. And then we converted the angle into radians, which is 0.85 radians, and then got the angular velocity of 1.7 radians per second. And then in order to solve for torque, we did inertia times angular velocity final minus inertia times angular velocity initial over time, and then got 14.82 newton meters. Okay, so now we're going to look at the knee torque calculation based off the same sketch that we did for the hip torque calculation. So we're pretty much going to do the same thing. We're going to calculate the inertia using the shank mass and shank radius of gyration squared, and then we're going to solve for both initial and final values. And then we're going to look at the angular velocity by using the difference in the angles of the shank, which was 110 degrees. Then we converted that to radians, which is 1.92 radians. And we found that the angular velocity is 3.84. And then we're going to use the same torque calculation that we did before. And then we found that the torque of the shank is about 12.75 newton meters. And this confirms what the literature shows because our torque of our hip is much greater than the torque of the knee.
So torques are also involved in action-reaction torques. This occurs when two torques are going in opposite directions and they cancel each other out to leave a zero change in momentum. So this occurs when the backswing of the arm of support leg is abducted and gradually adducts as the body moves through leg cocking and leg acceleration. At the same time, the trunk is also rotating and returns to neutral as the athlete progresses towards the ball. So you can see the first part of this on the left picture with the arm abducted. So the top half of the body is rotating one way, the bottom half is rotating the other way. And then on the right picture, both halves start twisting the opposite direction and come together. And so we think that with these canceling out, these help the athletes move forward and put all their force forward into their kick instead of having anything going off to the side. And it has been hypothesized that this technique helps provide a counterbalance to stabilize the body.
So now we're going to talk about the momentum-impulse relationship. Soccer players can choose how much force they want to enact on the ball by controlling the velocity of the leg they are contacting the ball with. Average contact time when kicking a soccer ball is 0.05 seconds when kicking the ball 30 meters per second. Initial velocity of a soccer ball is the same as the contact velocity of the kicking leg, and the momentum-impulse relationship is dictated by the contact time and the velocity of the kicking leg. In a study done, it shows that the ball impact lasts 10 milliseconds and occurs near the center of gravity of the foot. For a ball moving at 16.3 meters per second, the impact force of the foot is 1,200 newtons, but the peak foot impact force can reach as high as 2,900 newtons. So now we're going to do a sample problem using these numbers. So to calculate the impulse, we just did force times time. So we used the 1,200 newtons and the 0.1 second values to get 120 newtons per second. And then on the right, you can see that we showed the impulse momentum relationship, which is F times T equals mv. So we set mv equal to the impulse 120 newton seconds, and then use the velocity 16.3 meters per second. And then by doing this, we were able to show that the relationship is equal between impulse and momentum.
In conclusion, now I hope you have a better idea of the biomechanics that go into kicking a soccer ball. Thanks.